Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at conjugate acid-base pairs as well as amphiprotic species, which are vitally important in acid-base equilibrium. So a conjugate pair essentially is just an acid and its conjugate base, or a base and its conjugate acid. And the big thing about a conjugate pair is that they only differ by one proton. So in this example I have below with H2S, HS minus, and S2 minus, I have two conjugate pairs as well as something we call as an amphiprotic species. So the first thing I want to talk about is actually the conjugate pair. So when an acid loses a proton, it forms a base. So for instance, H2S can only act as an acid because it only has protons. It is not negatively charged. It couldn't accept a proton. So this is an acid. Now, when it turns into HS minus, it has donated an H plus to water. So it's classified as an acid, and now it's made HS minus, which has a negative charge. This is called its conjugate base, okay? Now this can act as a base because it has a negative, because it can now accept a proton. So this would be one acid-base conjugate pair, and it's, again, really simple. They differ by one H and then one positive or negative value depending if you're starting with an acid or a base. So again, when I go from the acid, I lose one hydrogen, so now I have one hydrogen, and because I've lost a positive, it is now -1. This is an acid-base conjugate pair. You can look these up in your acid-base table. They should be side by side. This one being the acid under the acid column, and this one being the base under the base column. Now, this HS minus has the ability to lose another proton. So even though it's classified as a conjugate base to H2S, it is actually an acid when referenced against S2 minus, because if it went from HS minus to S2 minus, it would have donated an H plus to water, and therefore it is classified as an acid. And S2 minus, because it now has a 2 negative charge, it can also act as a base. This is a conjugate base to HS minus. So I have two conjugate acid-base pairs here. I have H2S and HS minus. This is one acid-base conjugate pair, with this being the acid and this being the base. I also have HS minus and S2 minus as an acid-base conjugate pair, where this is the acid and this is the conjugate base. Okay, now these two, although they look similar, they both have S in them, they are not a conjugate pair. Because they differ by 2 protons, they are not a conjugate pair. Conjugate pairs can only differ by 1 proton. Now the other interesting thing here is HS minus in one scenario is acting as a base. Okay, so in red it's acting as the base, but in green it's acting as an acid. Whenever you have something that can do both jobs of being an acid or a base, it's considered an amphiprotic species. So an amphiprotic species can both donate a proton, at least one, so here's its proton, it could donate that, or it could accept a proton. Because it's negatively charged, it can accept. So we're going to spend more time later in the lesson talking about amphiprotics, but this is the first time we're going to see this. The most common amphiprotic species on Earth is actually water. It can both accept and donate a proton. That's why it can act as an acid or a base. So what I would like us to do right now, while this is fresh in our head, is I would like you to pause the video now and identify in this equilibrium equation, what is the acid, what is the base, what is the conjugate acid, what is the conjugate base. The acid and base are on the reactant side. The conjugate acid and the conjugate base are on the product side. Pause the video now and give it a try. Okay, now that you've had a chance to try the question, let's go through the answer. When I look at my reactants, the first thing I want to look for is anything that is definitely an acid and or is definitely a base. And in this question, I have actually both of those things. H2CO3 has two hydrogens that it could ionize. It is a diprotic acid. It does not have a negative charge. It cannot accept a proton. It cannot be a base. This here must be my acid. Now, F- does not have a proton to donate, so it must be a base. And if I look this up on my acid-base chart, which we're going to look at in just a moment, I would find H2CO3 only on the acid side of my table, and I would find F- only on the base side of my table. Now, the conjugates are the things that look similar but only differ by one proton. So for instance, this looks very, very similar to this. The only difference is that this now has an H, which is an extra proton, and not a negative charge because that proton is positively charged. This is a pair. This is the base, and this is the conjugate acid. Now, when I look at H2CO3, this is the acid. This looks very similar to HCO3-. It only differs by one proton and a positive or negative charge. This must be my conjugate base. So there are my two pairings. My pairings are H2CO3 and HCO3-. This is the acid and this is the conjugate base. And over here, I have F- and HF, where F- is the base and HF is the conjugate acid. I'd like to delve deeper into this question, so we're going to go to our data book on page 8 and 9 and check it out there. So looking at the acid and base table, you'll notice two titles. We have an acid formula and we have a conjugate base formula. So if I'm unsure if something is an acid-base conjugate pair, I can look them up here most of the time, but of course not all acids and conjugate bases are on this table, so I have to have a general idea of how this works. So for instance, if I was just to look at something like HSO3, its conjugate would have one less hydrogen, which is right here, yeah, and it has to have one more negative charge because it has lost a proton. So that would be an acid-base conjugate pair. Now, let's highlight or look at the ones that are concerned in our question, which was F-, which is up here. That was our base, and H2CO3 here. So in that acid-base reaction, we saw F- turn into HF because this was acting as the base, and this is now the conjugate acid. And we saw H2CO3 acting as the acid and turning into here into its conjugate base. So I would be able to look up the products of the reaction by looking at this table, highlighting or circling what I'm dealing with as reactants. There are my reactants. Then my products simply become the conjugates on this table. So it becomes very easy for me if I'm unsure of what to do. So for instance, I know that I have H2CO3 plus F-. And if I was unsure what are my products, I would simply go to H2CO3 and go, okay, what is its conjugate? It's HCO3-. And then I could look at F-, and then I could go across and say, oh, look, there is HF. So that's how you can use this table in one way, and I'm going to show you one more way of using this table. So in acids and bases equilibrium, and in all equilibrium, we have favorability. So one side of the reaction is favored over the other unless the K value is exactly 1. So as a reminder, if your K is greater than 1, you favor the products. And if your K is less than 1, you favor the reactants. Now, when you're dealing with an acid-base problem, you're often asked what side of this equilibrium is favored. And how you figure that out is using this table. And it's quite simple. Essentially, if your acid falls above your base on this table, it is going to favor the products. But if the base is above your acid on this table, it's going to favor the reactants. So for instance, the base is above my acid on this table. So I know that this reaction actually favors the reactants, that this is less than 50% forward, or I could say that the K is less than 1. Again, or I can say that this favors the reactants. Okay. We will be looking at favorability in more detail as we go through. One last thing I want to just point out in terms of this favorability is where strong acid and strong base lie on this table in relative to their other, whether it's acid or base. So for instance, all strong acids fall above all bases, which means if you have a strong acid as a reactant with any base, it will always favor the product side. This is also true with strong base. Strong base falls below every single type of acid, and therefore, if I have a strong base reactant with any acid, it will always favor the products. In our next section, we're going to look at something called an amphiprotic species. And being able to identify an amphiprotic species is extremely important. So an amphiprotic species is something that could act as a Bronsted-Lowry acid in one reaction and react as a Bronsted-Lowry base in a different reaction. Okay, so I break these down into kind of two major groups. One of them is just water. It is the most common amphiprotic species there is. The other grouping I have is the species needs to have a proton to donate. So whether it's monoprotic like H or diprotic like H2, that would have a hydrogen to donate. And then it also has to have a negative charge to accept. So this is the negative charge to accept, a negative charge to accept, two negative charge, that's a diprotic base, to accept two protons. Now, an exception to this rule, the way that this looks would be HCOO-. This would never donate. This would never act as an acid. Although it starts with that H is directly bonded to a C. This is a non-polar bond, and this thing could not be donated. This cannot act as an H+. The only way it could act as an H+ is if I had an H over on this side. This H could be donated if there was an H there, because that is a very polar bond and it could be released, but this one over here could not. Okay, so now I'm going to just do a little bit more of an explanation why. So the first thing I'm going to do is talk about each of these acting as a proton donor, acting as an acid. So if water was to donate a proton, it would be acting as an acid, and what would be left over of water would be OH-. That would be then the conjugate base to H2O. So again, if water donated a proton, it would be acting as an acid, and it would turn into hydroxide, which would be its conjugate base. We know that this happens because water reacts with bases to produce base, which is this conjugate base. Now, if I had Hx minus, X could be a number of different things here. It could be CO3 minus, it could be S minus, there's lots and lots of options. If it donated an H, it would be acting as an acid, and it would form X2 minus, which would be its conjugate base. This makes sense. X2 minus is a diprotic base. It could accept 2 protons. Okay, let's talk about these two things acting as a base. So if a hydrogen ion came in and was accepted by water, it would be acting as a base. It would produce H3O plus, which would then be its conjugate acid. Along with HX minus here, because it has a negative charge, it is attracted to positive things such as protons. So if it accepted an H plus, it would be acting as a base, and it would turn into H2X, which would be its conjugate acid. Okay, so this is how I break down identifying a amphiprotic species. And I'm going to show you now another way you can identify an amphiprotic species using your data book. As a fallback to figuring out if something is amphiprotic or not, and if you have a chart like this available to you, which you do at this level, but you probably won't at university, you can figure out something is amphiprotic if it appears on both sides of your acid-base table. So for instance, looking at oxalic acid, this is a diprotic carboxylic acid. It has 2 carboxylic groups. This H could be donated or this H could be donated. But they do it in a stepwise fashion, 1 proton at a time, and then the second proton after. So the conjugate base of oxalic acid is this ion here, HOOCCOO minus. This is the conjugate base. However, if you look, you will find this ion down here. It's called the hydrogen oxalate ion. It is also on the acid side of the table. So it's a base here, and it's an acid down here. So that means that this would have to be amphiprotic because it is both an acid and a base. Here's another example of it. Here is H2SO3. That's a diprotic acid as well. Its conjugate base is HSO3 minus. This is the conjugate base. Now, if this is a complete table, we should be able to find this somewhere below. I just have to keep searching for it. So let's look for HSO3 minus as we go down. Oh, and there it is as an acid. So here it is as an acid. Now I'll show you an example here, which we've already looked at, that just isn't complete on this table. And this is why it's really important for you to understand how to figure something out as amphiprotic or not by just looking at it. Okay, so when I look at this, I know this is amphiprotic because it has an H to donate and it has a negative to accept. But if I was to look just above this, you'd see this is a diprotic acid. It turns into HS minus. HS minus, which is in the example we started with, could donate a hydrogen, and it can also accept a hydrogen. But I can't find HS minus down here. That doesn't mean HS minus isn't amphiprotic. This table just can only handle so many acids and bases before you run out of space. So please, it is vital that you understand that when you look at a species, you can figure out whether it is amphiprotic or not, not using this table. And this table is not to be used as your primary way of figuring out amphiprotics. It's just to support you if you can find the acid in the question in this table. And again, I really want to push that when you get to university, it is very unlikely you will be given a table like this, and that you will only be given information for a question as it is needed. Before we start a couple of questions, I would just like to look at this table one last time to review a couple of important points. The first thing I'd like to look at is to make sure you understand the top 6 acids are your strong acids, and you can treat them as being equals in terms of ionization, the fact that they ionize 100%. Now, as you move down, the acids become weaker and weaker, and they become less strong. Now, what does that actually mean? When an acid becomes less strong, it ionizes less, which means it produces less hydronium. If you produce less hydronium, you're producing less acid, and therefore you're a weaker acid. These K values on the right-hand side tell you essentially how many products you have. And the product, of course, if you're looking at it in terms of acid, is H3O+. So if I was to look at this one here, the 5.6 times 10 to the negative 2, that slightly favors the reactant side, but it is still producing a lot of hydronium. As you move down, 10 to the negative 5 is less product, so I'm producing less hydronium, and therefore it is going to be less acidic. The converse is true. Down here, you have your strong base, and as you go up, you actually become a weaker and weaker base. Now, if you're looking at this value and going, well, 10 to the negative 13 is a smaller value than 10 to the negative 8, I need you to remember that Kb is equal to Kw all over Ka. These are Ka values. These are not Kb values. So roughly, if this is 10 to the negative 13, and this is just roughly, the Kb is going to be something like times 10 to the negative 1 or times 10 to the negative 2 in terms of being a base. So we actually get weaker moving up the table. So keep this in mind. If you have a really weak acid, this is the weakest acid other than water on this table, your conjugate base is very strong. This is essentially the strongest, weakest base. Conversely, if you have a very strong weak acid, which HOOCCOOH is, then you have a very weak conjugate base. The conjugate base here is going to have a Kb somewhere in the region of times 10 to the negative 12 or times 10 to the negative 13, something like that. That's just rough off the top of my head. In this next section, we're going to look at a couple of questions to summarize everything that we have learned in this lesson. So what I would like you to do is pause the video now and try the questions, and then unpause it and come back and we'll go through it. So pause the video now. Now that you've had a chance to try the question, let's go through the problem. The first thing we would want to do is address the reactants as either an acid or a base. And what I'm looking for is clarity to whether something is definitely an acid only, definitely a base only, or an amphiprotic species. I always want to identify the things I know for sure as an acid or base first. So H2SO3 can only act like as an acid since it only has protons to donate. This would be classified as a weak diprotic acid because it does 2 hydrogens present. What I want to do to figure out its partner or conjugate is to find the species on the product side that looks almost identical, other than it will have 1 less proton if it's going to be the conjugate base. And so when I look on the product side, this almost looks identical to H2SO3, except it's down 1 proton, which is 1 less hydrogen, and it has become negatively charged because the proton did have a positive charge, so it has to be 1 more negative now. This would be our conjugate base. When you look at NO2-, this could only act as a base because it does not have a proton to donate and it is negatively charged. I could also look this up on my acid and base chart. So the NO2- is a base, And if I look for its partner, which looks very similar, it should have one more proton, which it does because it's an acid. This is the conjugate acid. So there is my other pair. So based on what we've done so far, the acid is H2SO3. The conjugate base is HSO3 minus. The base is NO2 minus, and the conjugate acid is HNO2. Now, the next part says the strongest acid is and the strongest base is. And they also talk about amphiprotic species, whether there are any, and then some favorability. So in order to answer these questions, I'm going to go to my acid and base chart. So to answer the next questions, we are going to go to our table and find our acid and our base. So our acid was sulfurous acid, which would be found here. Here's my acid, and it turned into my conjugate base, HSO3 minus. And I'm going to find my base, which was NO2 minus. And it turned into its conjugate acid here. So the first question I'll ask is, or answer, is just the favorability of the reaction. Because the acid falls above the base, I know that this is going to favor the products, that the K is going to be greater than 1, or I could say that it's greater than 50% forward. Now, the other question which was what is the strongest acid, what is the strongest base, and amphiprotic species, I will deal with now. So acids get stronger as you move up this table, and the two acids that we had were HNO2, this was a product, and H2SO3, which was the reactant. Because HSO3 is farther up the table, this is the strongest acid out of the two. In terms of strongest base, we had two bases, NO2 minus and HSO3 minus. Bases get stronger as you move down the table. So out of HSO3 minus and NO2 minus, the stronger of the two would be NO2 minus. This would be the strongest base. The last question was, are there anything that is amphiprotic? So in order to be amphiprotic, you must have a negative charge and you must have a hydrogen to donate. So if I look at H2SO3, it only has protons to donate. It does not have a negative charge. That is not amphiprotic. When I look at HNO2, it only has a hydrogen to donate. It does not have a negative charge to accept. It is only an acid. When I look at NO2 minus, it has no H to donate, but it has a negative to accept. It's only a base. But when I look at HSO3 minus, it has a hydrogen to donate, and it has a negative to accept. So therefore, HSO3 minus is amphiprotic. Now, if this table is complete, I should be able to find HSO3 minus somewhere on the base side of the table. And if I move down, you will find it here. Because it is on both sides of the table, it's both acting as an acid or a base, and therefore it is considered amphiprotic. To complete the rest of the table, we'll just fill it in with our answers. Our strongest acid was H2SO3. The strongest available base was NO2 minus. The amphiprotic species was HSO3 minus. We figured out that the reaction favors the products and that the K is greater than 1. And we can also say that the reaction was 50% forward, or well, more than 50% forward. I'd like you to try one more question before the end of our lesson. Please pause the video now and try to answer the following questions. So let's review this question. The first thing I'd want to know is there anything in here that is definitely an acid or definitely a base? When I look at this HOOC COO minus, I recognize that this thing is actually amphiprotic. It could donate this H as part of the carboxylic group. It could also accept a proton here, so it could be a base. So I'm not going to address this one yet because I'm going to look at the other reactant. It might tell me what it actually is acting like. So for instance, H3PO4 can only act as an acid. It is a triprotic acid because it has 3 hydrogens. It has no negative charge. So this must be the acid. Now the thing that looks like it is H2PO4 minus. So this must be the conjugate base. These differ by 1 proton. The H3PO4 has lost a proton, so therefore it must be an acid. This is a conjugate base. It can act like a base because it has a negative charge. That by default makes this the base, but I can confirm that when I look at the 2 species and I compare them. So this looks like this. It differs by 1 proton. But what I'll notice when I go from here to here, I can see that it has accepted an H+, which would be this hydrogen here. Now, if you've accepted an H+, then you have to be a base. So this would be the conjugate acid. So let's put those in. The acid would be H3PO4. The conjugate base would be H2PO4 minus. The base is HOOCCOO minus, and its conjugate acid is HOOCCOOH. Now, in order to answer the rest of these questions, I am going to go to my table and look these species up. So, I'm going to find HOOCCOO minus in 2 spots, here and here. That means that it's amphiprotic. But what I also have to recognize is in my chemical reaction I was just dealing with, I was dealing with it as a base. So I must be using this when I'm trying to figure out favorability and not this. My base was H3PO4, which is right here. So I'm going to highlight all the things that are involved. This turned into this. This was my acid. This is the conjugate base. This was my base, and it's turning into a conjugate acid. Because the base was above the acid, this would favor the products. This would have a K less than 1. It would be in equilibrium, but it would be, the reaction would be less than 50% forward. Okay. Now, the strongest acid is highest up on the left-hand side. So the strongest acid in the equation is HOOCCOOH. That's my strongest acid. My strongest base is furthest down the right, so that would be H2PO4 minus. This would be the strongest base. Let's go back to our page and fill in the answers. Okay, so our strongest acid was HOOCCOOH. The strongest base was H2PO4 minus. My amphiprotic species are, there's actually 2. We addressed this one, HOOCCOO minus. We said that it could donate this hydrogen, and it could accept here. But H2PO4 minus is also amphiprotic. It actually has the ability to donate 2, so it's a diprotic acid. It has the ability to accept 1, it's a monoprotic base. And because it can do both, it's amphiprotic. So it falls under a lot of different categories. Now again, because our base was above the acid, this is going to favor the reactants. The K is going to be less than 1, and the reaction is going to be less than 50% forward, or I could say it like this, K is less than 1. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.